It's great to speak to you about your innovation based on neodymium, a rare earth. I think everybody would say that they don't quite know where these are, but I'm certain that we would notice if they didn't exist, because they are ubiquitous in so many things that we're using today. What I would be interested to ask you first is, what led you to move away from the research on conventional magnets and see the possibilities of using rare earth metals to create a permanent magnet?
When I started with the research of samarium cobalt magnet, as I joined the company, and I was told that I need to do work on research to improve this. And in this process, I realized that the cobalt, which was being used for the magnet, was very expensive. And it was very scarce because it can only be sourced from Congo, which was a conflict-ridden region. So the supply was very unstable. And I had recognized this issue. And I had thought about, well, why not use iron instead, which could give a better magnetic property for the overall magnet? Because if you compare cobalt and iron, if you look at the smallest unit of magnetism, what we call the magnetic moment, it's only cobalt is only 70% of iron. So if we could use iron instead, we will see, and I had anticipated that we will have higher magnetic strength. So based on these two aspects, I had looked into researching and finding a compound which uses rare earth and iron. And I recognized that perhaps this could be the needs for people. And this is something that's required and needed in the world. And that was the start of my research.
What I'm interested to know is, when did you actually realize the benefits of using a powdered metallurgical manufacturing process to produce a sintered magnet? That process is unique, I think, to you.
So when I looked into rare earth magnets in combination with iron instead of cobalt, my first step was to find a compound that's appropriate. The known elements that they were used with rare earth was not magnetic at all. So everything had to start with finding the appropriate compound. I had a clue, a hint from through my research that neodymium and iron could work, and that's why I came to find the neodymium iron and boron compound. But it's not enough just to find the compound itself, because you need to have the compound to apply magnetic coercive force. In order to do that, you need to have the microstructure that's appropriate to have those magnetic properties. And so that's why we needed to look into the production process. And for that, we came to find this particular process that we're talking about with sintering. So first of all, you have the compound, you pulverize it, and you get the directions all aligned. Then you press, and then you go through sintering. Once you go through this process, we find that it will give you the most appropriate microstructure to give the material magnetism, and it will be appropriate for magnets. And that I would think came through our research and eventually led to the success of the research itself.
Can I ask you finally, what actually makes the Queen Elizabeth Prize for Engineering a special award to you? You've had many awards. I would love to know what makes this particular award special for you.
This award, I admire specifically that it's an engineering award. And personally, of course, I'm very happy to be awarded this. But to put the focus on engineering, and this engineering is always for others, for people. That's why we exist. That's why we do engineering. And this award really influences people, and get people noticing about how important engineering is.
Dr. Sagawa, thank you very much for being with me and answering all these questions.
Thank you.